Welcome to Dormant Knowledge. I'm your host, Deb, and this is the podcast where you'll learn something fascinating while gently drifting off to sleep. Our goal is simple: to share interesting stories and ideas in a way that's engaging enough to capture your attention, but delivered at a pace that helps your mind relax and unwind. Whether you make it to the end or drift away somewhere in the middle, you'll probably absorb some knowledge along the way. Tonight, we're exploring one of the most iconic inventions in human history, Thomas Edison's incandescent light bulb. But, as we'll discover, the story is far more complex and fascinating than the simple narrative of Edison invented the light bulb. It's actually a tale of methodical experimentation, fierce competition, brilliant engineering, and some rather ruthless business practices. Before we get started, if you like what we are doing here and this is working well for your nighttime routine, we hope you will consider supporting this fun project so that we can keep it going. You can find us online at dormantknowledge.com, where you can sign up for our newsletter. You can also find us on social media at Dormant Knowledge on Instagram and Facebook, or at dormant_knowledge. That's DRMNT_knowledge on X. So settle in, get comfortable, and let's begin our journey into the illuminating world of Edison's greatest triumph. You know, it's hard for us to imagine what the world was like before electric lighting. I mean, really hard. We flip a switch and instantly have bright, clean, controllable light. But in the 1870s, when Edison was beginning his work on incandescence, most people lived in a world that was, frankly, quite dim after sunset. Picture this. It's 1878, and you're walking through the streets of New York in the evening. The main thoroughfares might have some gas lamps, those flickering yellowish flames that cast dancing shadows, and occasionally exploded. Actually, gas explosions were terrifyingly common. The gas was stored in large underground mains, and leaks were, let's just say they were an occupational hazard of urban living. Inside homes, people relied on kerosene lamps, candles, or, if they were wealthy, gas fixtures. But think about what this meant for daily life. Most people went to bed shortly after sunset simply because there wasn't enough light to do much else. Reading by candlelight or oil lamp was possible, but it was dim, smoky, and actually quite dangerous. House fires from overturned lamps or candles were incredibly common. The wealthy might have had gas lighting in their homes, but even that was problematic. Gas flames consumed oxygen, produced carbon monoxide, and made rooms uncomfortably hot. Plus, the light was still relatively dim and couldn't be easily controlled. You couldn't just flip a switch. There were some early forms of electric lighting, actually. Arc lights had been around since the early 1800s. These produced incredibly bright light by creating an electrical arc between two carbon electrodes. But they were completely impractical for most uses. Imagine trying to read a book by the light of a small sun. Arc lights were so bright, they were mainly used for lighthouses, street lamps, and large public spaces. You certainly couldn't have one in your living room. So this was the world Edison was trying to illuminate, literally. A world where most human activities stopped at sunset, where reading after dark was a luxury, and where the smell of gas or the smoke of oil lamps was just part of life. But Edison saw something different. He envisioned what he called subdivided electric light, small, controllable, pleasant electric lights that could be used in homes and offices, lights you could turn on and off individually that didn't smoke or smell or consume oxygen. It sounds simple now, but the technical challenges were, well, they were enormous. Now, here's where things get really interesting from a scientific perspective. Edison wasn't just randomly trying different materials and hoping something would work. Well, okay, there was some of that, but he also understood the fundamental physics problem he was trying to solve. Let me explain what incandescence actually is, because it's quite elegant when you think about it. When you pass an electric current through any material that offers resistance to that current, that material heats up. This is called Joule heating, named after James Prescott Joule. The electrical energy is converted to thermal energy, heat. Now, as any material gets hot enough, it starts to glow. This is called incandescence, from the Latin incandescere, meaning to glow with heat. The color and intensity of that glow depend on the temperature. You've probably seen this with a piece of iron in a blacksmith's forge. First, it glows red, then orange, then yellow, then white as it gets hotter. This follows what we call Planck's law of blackbody radiation, though Planck wouldn't formulate this until 1900, well after Edison's work. But the basic principle was understood. Hotter objects emit more light and shift toward the blue end of the spectrum. So Edison's challenge was to find a material that could be heated by electricity to temperatures high enough to produce useful light. We're talking about 2,000 to 3,000 degrees Fahrenheit without melting, burning up, or otherwise failing. But here's the tricky part. Most materials, when heated to those temperatures in the presence of oxygen, will simply oxidize, basically burn up. Carbon, for instance, will combine with oxygen to form carbon dioxide and just disappear as gas. So Edison knew he needed to create a vacuum inside his bulbs, removing as much air as possible. Even in a vacuum, though, materials face other challenges. At those extreme temperatures, atoms start moving around more energetically. In metals, this can cause what we call electromigration. The metal atoms actually start moving along the direction of current flow, causing the filament to develop weak spots and eventually break. Edison tried literally thousands of materials, and I mean literally. His notebooks document tests of over 3,000 different substances. Platinum was one of his early favorites because it has an extremely high melting point, 3,215 degrees Fahrenheit. But platinum is expensive, and even worse, it has this annoying property where it absorbs gases at high temperatures and then releases them, which compromised his vacuum. So he tried iridium, which is even more expensive than platinum. He tried various metal alloys. He tried different forms of carbon, lamp black, carbon from gas flames, carbon from oil flames. Each material presented its own unique failure mode. The breakthrough came when he started experimenting with organic materials that he carbonized. Essentially, he would bake organic matter in the absence of oxygen until only the carbon structure remained. This carbonized material had a very different structure than pure carbon. It was more porous, more resilient, and interestingly, it seemed to handle thermal stress better. His first major success was with carbonized cotton thread, but the real breakthrough, the one that made commercial light bulbs possible, came from an unlikely source: bamboo. Now, bamboo might seem like a random choice, but there's actually brilliant materials science behind it. Bamboo has these long, continuous fibers running through it. When carbonized, these fibers create a carbon structure that's incredibly strong and uniform. The carbon fibers in carbonized bamboo are aligned in the direction of current flow, which reduces resistance and hot spots. Edison's team tested bamboo from all over the world. They found that bamboo from Japan, specifically from near Kyoto, had the ideal fiber structure. These bamboo filaments could burn for over 1,000 hours, which was, well, it was revolutionary. But even with the right material, there were still engineering challenges. How do you connect these fragile carbon filaments to the electrical circuit? How do you mount them inside a glass bulb? How do you create a reliable vacuum? Edison developed this entire ecosystem of technologies: vacuum pumps, glass blowing techniques, electrical connections that could maintain a seal. Actually, one of the most ingenious aspects of Edison's design was how he dealt with thermal expansion. As the filament heats up, it expands. As it cools down, it contracts. This constant expansion and contraction would normally cause the filament to break, but Edison designed his filaments in a loop shape, and he mounted them with just enough slack that they could expand and contract without breaking the electrical connections. The final design was elegantly simple: a carbonized bamboo filament shaped in a horseshoe loop mounted inside an evacuated glass bulb with electrical connections sealed through the glass. It's simple to describe, but representing years of methodical experimentation and brilliant problem solving. Now, here's something that often gets lost in the popular telling of the story. Edison wasn't working alone in a vacuum, so to speak. There were other brilliant inventors and scientists all over the world working on the same problem. In England, there was Joseph Swan, Sir Joseph Wilson Swan, who was actually working on incandescent lighting before Edison. Swan had developed a working incandescent lamp by 1878 using carbonized paper filaments. His early demonstrations in Newcastle upon Tyne were quite impressive, actually. But Swan faced the same challenges Edison did with creating reliable, long-lasting filaments and achieving good vacuum technology. So, sorry. What's fascinating is that Swan and Edison were solving the same technical problems independently, often coming up with very similar solutions. Both realized the need for high resistance filaments. Both worked with carbonized organic materials. Both understood the necessity of creating good vacuums. In fact, Swan's approach was in some ways more scientifically rigorous than Edison's. Well, Edison was famously, somewhat dismissive of theoretical science. He preferred trial and error to mathematical analysis. Swan had a stronger background in chemistry and physics. He understood the theoretical principles behind what he was doing. The irony is that Swan probably deserves equal credit for inventing the incandescent light bulb, but he lacked something Edison had in abundance: business acumen and publicity skills. Swan was content to demonstrate his invention to scientific societies and slowly improve his designs. Edison, on the other hand, was making grand public pronouncements and promising to light up entire cities. Actually, they eventually ended up working together. In 1883, Edison and Swan formed a joint company in Britain called Edison and Swan United Electric Light Company, which was often shortened to Ediswan. But by then, Edison's name was already synonymous with the light bulb in the public mind. There were others, too. Heinrich Goebel, a German-born American, claimed to have developed incandescent lamps as early as 1854 using carbonized bamboo filaments inside glass bulbs. His claims were, they were disputed, and he didn't have the documentation or publicity that Edison did. But some historians think Goebel might have been 25 years ahead of everyone. Hiram Maxim, yes, the same Hiram Maxim who later invented the machine gun, was working on carbon filament lamps in the late 1870s. His approach was quite different. He used carbon deposited from hydrocarbon gas flames. Maxim actually held several important patents related to incandescent lighting. And then there were the arc light pioneers who were trying to make their intensely bright lights more practical for indoor use. Charles Brush in Cleveland was doing remarkable work with arc lighting systems. Paul Yablokov in Paris had developed what he called electric candles, essentially arc light candles that burned more steadily. What's interesting is how these inventors influenced each other. Even when they were technically competitors, information traveled through scientific journals, patent applications, and personal correspondence. Edison was quite good at, shall we say, borrowing ideas from other inventors and improving upon them. This wasn't necessarily unethical by the standards of the time, but it does complicate the narrative of Edison as the sole inventor of the light bulb. The truth is, the incandescent light bulb was invented by many people over many years, with each inventor solving different pieces of the puzzle. Edison's genius was in putting all the pieces together into a practical commercial system and then marketing it brilliantly. I am going to take a quick break, and then we'll continue our story with Edison's invention factory. I'm back, and if you're still with us, let's talk about Menlo Park, because this is where the magic really happened. Edison established what he called his invention factory in Menlo Park, New Jersey in 1876. It was revolutionary, because before Edison, most inventors worked alone in their workshops, but Edison created the world's first industrial research laboratory. Picture this: a complex of buildings housing machine shops, chemical laboratories, a library, and dormitories for workers. Edison employed about 30 people: machinists, chemists, glassblowers, clockmakers. He called them his muckers, which was actually a term of endearment. These weren't just employees. These were collaborators in the invention process. Edison himself he was quite a character. He was partially deaf, which actually might have helped his concentration. He could tune out distractions and focus intensely on problems. His work habits were legendary and probably not very healthy. He would work 18 to 20 hours a day, taking short naps on a cot in his laboratory when exhaustion overcame him. He had this philosophy that genius was 1% inspiration and 99% perspiration. And he lived by that motto. When working on the light bulb, he would often work for days at a time with just brief breaks for sleep. His deafness had some interesting effects on his work style. He couldn't easily participate in conversations, so he communicated a lot through written notes. This actually created a fantastic historical record. There are thousands of pages of notes and sketches from Menlo Park documenting the invention process. Edison was also surprisingly hands-on for someone who's remembered as the great inventor. He wasn't just sitting in an office directing others. He was in the workshop, conducting experiments himself. His notebooks showed detailed observations about filament behavior, vacuum levels, electrical measurements. But here's something that often gets overlooked. Edison didn't work alone. The light bulb was really invented by a team. Francis Upton, a Princeton-trained mathematician, handled much of the theoretical work that Edison found tedious. Charles Batchelor was Edison's right-hand man, an extraordinarily skilled machinist who could build almost anything. John Crucy was the master machinist who turned Edison's sketches into working prototypes. There's a famous story, probably apocryphal, but it illustrates Edison's method about how he would test job applicants. He would take them to lunch and watch to see if they salted their food before tasting it. If they did, he wouldn't hire them because it showed they made assumptions before gathering data. Whether or not the story is true, it captures Edison's obsession with empirical observation. Edison was also quite superstitious in his way. He believed that the best ideas came to him in the moments between waking and sleeping. He would sometimes nap in his chair, holding steel balls in his hands. When he started to fall into deep sleep, the balls would drop and wake him, and he would immediately write down whatever thoughts were in his mind. The social dynamics at Menlo Park were fascinating. Edison was the undisputed leader, but he encouraged his team to challenge ideas and suggest improvements. They would work together on problems, often staying up all night when they were close to a breakthrough. During the light bulb project, the entire team became obsessed with finding the perfect filament. They would test materials during the day, analyze results in the evening, and plan the next day's experiments late into the night. It became an all-consuming quest. Edison's personality had both inspiring and problematic aspects. He was incredibly driven and could motivate his team to achieve things they didn't think were possible. But he was also quite ruthless about taking credit for work that was often collaborative. Most of the patents from Menlo Park list Edison as the sole inventor, even when the work was clearly done by teams. This team approach to invention was actually Edison's greatest innovation in many ways. The light bulb wasn't just the product of one man's genius. It was the product of systematic, organized research and development. Edison essentially invented the modern R&D laboratory. Now, here's where Edison really showed his genius, and it wasn't just in the laboratory. Edison understood something that many inventors didn't. Creating a new technology isn't enough. You have to create an entire system around it, and you have to create a market for it. Think about it. What good is a light bulb without electricity to power it? And what good is electricity without a distribution system to deliver it? And what good is a distribution system without customers who want to buy your product? Edison realized that to make electric lighting commercially viable, he needed to create what we would now call an integrated solution. He needed to generate electricity, distribute it, measure consumption, and provide all the components, not just light bulbs, but switches, wiring, meters, even the electrical outlets. In 1882, Edison opened the Pearl Street Station in Lower Manhattan. This was the world's first central power plant designed to provide electricity for lighting. It's hard to overstate how revolutionary this was. The idea of generating electricity in one location and distributing it to multiple customers was completely new. The Pearl Street Station served about 400 customers initially, providing power for about 10,000 light bulbs. Edison chose this location carefully. It was in the heart of New York's financial district, serving customers who could afford this new luxury and whose businesses would benefit from extending operating hours. But the engineering challenges were enormous. Edison had to design not just the power plant, but the entire distribution system. How do you run electrical cables under city streets? How do you regulate voltage? How do you measure how much electricity each customer uses? How do you make it safe? Edison's team developed underground cable systems, electrical meters, voltage regulators, safety switches. Essentially, they invented the entire infrastructure of electrical utilities, and they did it while the technology was still being perfected. Edison's business model was quite clever. Instead of just selling light bulbs, he sold complete electrical systems. He would contract with cities or large buildings to install entire electrical systems, generators, wiring, switches, meters, and, of course, light bulbs. This meant ongoing revenue, not just one-time sales. He also understood the importance of public demonstrations. Before the Pearl Street Station opened, Edison staged dramatic public exhibitions. He would light up entire buildings or streets, showing off the safety and convenience of electric lighting compared to gas. One of his most famous demonstrations was at the 1881 International Electrical Exhibition in Paris. Edison's exhibit featured a massive display of light bulbs that could be controlled individually, something that was impossible with gas lighting. Visitors were amazed by the ability to turn lights on and off instantly, without matches or flames. But Edison's business practices were, well, let's say they were aggressive. He was quite ruthless about protecting his patents and eliminating competition. He would file lawsuits against competitors, sometimes on questionable grounds, knowing that the legal costs would drive smaller companies out of business. He also had a talent for self-promotion that bordered on, well, on shameless marketing. Edison understood that in the emerging mass media age, perception was often more important than reality. He cultivated relationships with newspaper reporters, staged publicity events, and made grand promises about the future of electricity. For instance, Edison famously promised that he would make electricity so cheap that only the rich would burn candles. This was a brilliant marketing slogan, but it was also a promise that took decades to fulfill, if it ever was truly fulfilled. Edison's approach to manufacturing was also innovative. Instead of licensing his technology to other manufacturers, he built his own factories. He controlled every aspect of production, from raw materials to finished products. This vertical integration allowed him to maintain quality control and maximize profits, but it also required enormous capital investment. The scale of Edison's vision was remarkable. He wasn't just thinking about individual light bulbs. He was imagining entire cities powered by electricity. He was thinking about how electric lighting would change human behavior, extend working hours, make cities safer at night. And he was largely right. Electric lighting did transform urban life in ways that went far beyond just providing illumination. It enabled the growth of department stores, restaurants, and entertainment venues. It made cities safer by eliminating the dark corners where crime flourished. It extended the productive day for millions of workers. But Edison's success as a businessman also created problems that would later haunt him, particularly in his conflicts with other inventors and entrepreneurs who had different visions for how electricity should be generated and distributed. After this short break, we'll come back with the more ugly side of the story of the light bulb. That music just about put me to sleep. But if you're still awake, let's get back to what might be the most fascinating and contentious part of Edison's story: his battles with other inventors and scientists. These weren't just friendly professional disagreements. They were full-scale wars involving patents, publicity, and, well, some rather unsavory tactics. The most famous of these conflicts was what became known as the War of Currents: Edison's direct current system versus the alternating current system promoted by George Westinghouse and Nikola Tesla. Let me explain the technical difference, because it's important. Edison's system used direct current, DC, where electricity flows in one direction at a constant voltage. This was relatively simple and safe for the low voltage applications Edison was designing. His light bulbs, his distribution system, his meters, everything was designed around DC power. But DC had a significant limitation. It couldn't be transmitted efficiently over long distances. The voltage would drop off and you'd lose a lot of power. This meant that power plants had to be located within about a mile of their customers. For dense urban areas, this might work, but it made electricity impractical for rural areas or for transmission between cities. Alternating current, AC, solved this problem. With AC, you can use transformers to step voltage up for long-distance transmission, then step it back down for safe use in homes and businesses. Westinghouse and Tesla understood that AC would allow for much larger, more efficient power plants serving much wider areas. Edison initially dismissed AC as impractical and dangerous, but I think his opposition was as much about business as about technology. Edison had invested enormous amounts of money in DC technology. His patents, his factories, his installed systems, everything was based on direct current. Switching to AC would have made much of his investments obsolete. So Edison launched what can only be described as a propaganda campaign against AC power. He emphasized the dangers of high voltage alternating current, which were real. AC at high voltages is indeed more dangerous than DC at low voltages. But Edison's tactics became increasingly questionable. He staged public demonstrations where he electrocuted animals, dogs, cats, even an elephant named Topsy, using AC current, trying to prove the AC was too dangerous for public use. These demonstrations were, they were gruesome and scientifically questionable, since he was using much higher voltages than would typically be found in homes or businesses. Edison even promoted the use of AC current for executions, helping to develop the electric chair. His reasoning was cynical. If AC was associated with death and execution, the public would be less likely to accept it for lighting their homes. The conflict with Tesla is particularly interesting because Tesla had actually worked for Edison briefly. Tesla was a brilliant Serbian-American inventor who understood AC systems far better than almost anyone else. When he first arrived in America in 1884, he worked at Edison's Menlo Park laboratory. But their working relationship was, it was problematic. Tesla was theoretically minded, interested in elegant mathematical solutions. Edison was empirically minded, preferring trial and error. Tesla would later describe Edison as having a veritable contempt for book learning and mathematical knowledge. There's a famous and probably somewhat exaggerated story about their conflict. Tesla claimed that Edison promised him $50,000 if he could redesign Edison's DC generators to make them more efficient. Tesla did the work, but when he asked for payment, Edison allegedly said, "Tesla, you don't understand our American humor." Whether or not this story is accurate, Tesla did leave Edison's employment and eventually partnered with Westinghouse to develop AC power systems. This put him in direct competition with his former employer. Edison's patent wars weren't limited to the AC-DC conflict. He was constantly involved in litigation over light bulb patents, power generation patents, and electrical distribution patents. His legal strategy was often to file broad patents and then sue anyone who developed similar technology. One of the most significant patent battles was with Joseph Swan, whom we discussed earlier. Swan held important patents on incandescent lighting in Britain, and when Edison tried to expand internationally, he found himself in complex legal battles over who had invented what and when. Edison's approach to these patent conflicts was, it was sophisticated and ruthless. He would often buy up patents from other inventors, not necessarily because he needed the technology, but to prevent competitors from using it. He would also file numerous patents on minor variations of technologies, creating what we might now call a patent thicket, making it nearly impossible for competitors to develop products without infringing on some Edison patent. Or papers. But perhaps the most troubling aspect of Edison's competitive tactics was his willingness to use personal attacks and misinformation. He would spread rumors about competitors' financial stability, question their technical competence, and even make personal attacks on their character. The irony is that Edison ultimately lost the war of currents. AC power proved to be superior for large-scale electrical distribution, and by the 1900s, even Edison's own companies had largely switched to AC systems. Westinghouse and Tesla's vision of centralized power plants serving wide areas through AC transmissions became the standard that we still use today. Edison's reputation suffered from these conflicts. His tactics were seen as increasingly desperate and unethical. The man who had been celebrated as America's greatest inventor was now seen by many as a ruthless businessman who put profits ahead of scientific progress. As we near the end of our journey through Edison's illuminating story, it's worth reflecting on the lasting impact of his work and separating the myths from the reality. First, let's address the biggest myth. Edison invented the light bulb. As we've seen, this is a dramatic oversimplification. Incandescent lighting was developed by many inventors over many years. Edison's contribution was creating a practical, commercially viable system and then marketing it brilliantly. What Edison truly invented was the modern system of electrical utilities. The idea of generating electricity in central plants and distributing it to multiple customers. That was Edison's vision, and it transformed the world. The impact of electric lighting on human civilization is hard to overstate. Before Edison's work, human activity was fundamentally constrained by daylight. People went to bed shortly after sunset and woke with the dawn because there simply wasn't adequate artificial lighting for most activities. Electric lighting changed all of that. Suddenly, factories could operate multiple shifts. Stores could stay open in the evening. People could read, study, and socialize after dark. The rhythm of human life, which had been tied to the solar cycle for millennia, was suddenly liberated. But there were unintended consequences too. Electric lighting contributed to what we now recognize as disrupted sleep patterns. The human circadian rhythm evolved to respond to natural light cycles, and bright artificial lighting, particularly in the evening, can interfere with the production of melatonin and other sleep-regulating hormones. More papers. Urban development was transformed as well. Electric street lighting made cities safer and more pleasant after dark. This enabled the growth of nighttime entertainment districts, late-night dining, and what we might call nightlife as a cultural phenomenon. The economic impact was enormous. Industries that had been limited to daylight hours could now operate around the clock. Productivity increased dramatically. The growth of department stores, which relied on attractive lighting to display merchandise, was made possible by electric lighting. Edison's approach to invention, systematic, team-based research and development, became the model for modern industrial research. The idea of the corporate R&D laboratory, where teams of specialists worked together on complex technical problems, was pioneered at Menlo Park. But Edison's legacy is complicated by his business practices and his resistance to superior technologies like AC power. His willingness to use questionable tactics against competitors, his sometimes unethical treatment of employees and partners, and his tendency to take credit for collaborative work, these aspects of his character complicate the heroic narrative. There's also the question of how Edison's fame overshadowed other inventors. Joseph Swan, Heinrich Goebel, Hiram Maxim, and others made significant contributions to incandescent lighting, but they're largely forgotten, while Edison is remembered as the sole inventor. The myth-making around Edison began during his lifetime and was actively promoted by Edison himself. He understood the value of publicity and cultivated an image as the Wizard of Menlo Park, a solitary genius who could invent anything. This image was powerful and compelling, but it wasn't entirely accurate. In popular culture, Edison became the archetype of the American inventor, the self-made man who could solve any problem through hard work and ingenuity. This narrative appealed to American values and individualism and entrepreneurship, but it obscured the collaborative nature of technological innovation. Modern historians have worked to provide a more nuanced view of Edison, recognizing his genuine contributions while also acknowledging his limitations and the contributions of others. Edison was brilliant, hardworking, and visionary, but he was also human, with all the flaws and contradictions that implies. Perhaps the most important lesson from Edison's story is that technological innovation is rarely the work of individual genius. It's usually the result of many people working on similar problems, building on each other's work, sometimes competing and sometimes collaborating. The incandescent light bulb was invented by a community of inventors, not by one man working alone. Edison's light bulb, or more accurately, the electrical lighting system that Edison and his contemporaries developed, remains one of the most transformative technologies in human history. It extended the useful day, made cities safer, enabled new forms of commerce and entertainment, and fundamentally changed the rhythm of human life. Every time you flip a light switch, you are participating in a technological system that traces its roots back to those long nights at Menlo Park, where Edison and his muckers tested thousands of materials, solved countless engineering problems, and gradually brought electric light to the world. The story of Edison's light bulb is ultimately a story about human ingenuity, persistence, and the complex interplay between invention and business. It's a reminder that behind every technological revolution, there are real people solving practical problems, often working collaboratively, sometimes competing fiercely, but always pushing forward the boundaries of what's possible. Thank you for listening to Dormant Knowledge. If you're still awake and hearing my voice, I appreciate your attention. But if you've drifted off to sleep somewhere along the way, which was partly the goal, then you won't hear me saying this anyway. Either way, I hope some knowledge about Edison's remarkable journey from darkness to light has made its way into your consciousness, or perhaps your dreams. Until next time, this is Deb, wishing you restful nights and curious days.